This video we are studying dimensional analysis. And in dimensional analysis, we are studying physical quantities in line with their units and dimensions. So first of all, we are going to start by having some physical quantities, that is derived quantities, and we are going to see how their dimensions are gotten. Now, the major dimensions are from the units of length, mass, and time. These are the three major dimensions that we look at, and these are physical quantities. So these are their symbols: capital L for length, capital M for mass, and capital T for time. So that is what we are going to be using to do dimensional analysis. Now let's take a physical quantity like volume, for example. When we have volume and we are to get its dimension, what we are going to see is that from the formula of volume, volume is length times width times breadth. That's length times width times the breadth or height. Then from this, these are all measurements of length. We are measuring length, we are measuring width is a length, the height or breadth is a length. So we can see that dimensionally the volume is equal to L cube. That is three lengths, three different kinds of lengths times 3. Okay, so let's see something like area. We know that area is length times width, right? So I know you guessed as much. So length squared. A length times another length squared. Now let's get to something like velocity or speed. Velocity or speed. Now by formula, velocity or speed is displacement or distance over time. So whether it's displacement, that's for velocity, or distance for speed over time. So distance is a measurement of length. Time is a measurement of time, of course. So this is the dimension. And we usually write it in a single line, not as a fraction like this. So in a single line, we have length and then time raised to power minus 1 to show that it was a denominator. So whenever we have any quantity down here, we have to use negative and then the power. It is raised to, so this t was raised to power 1, so we have to raise it to power negative 1. So this is how dimensions are gotten. Now let's get to more complex things. We have that acceleration is equal to velocity over time. So we've already gotten that the dimension of velocity is length per unit time. So over time, another time down here. And we can't leave it as a fraction like this. So now we now have 2 times under, we have length times time negative 2. Why? Because there are 2 times like as a fraction. I should have just started with velocity is equal to length over time, and since over time again, so we now have another time down here. So that means we have time squared down here. So we have length per unit time squared. Okay, so that is acceleration. Now let's get dimension of force. So by now you already know the drill. If you're told to get the dimension of any physical quantity, what you're going to start with is with the formula. We have that force is equal to mass times acceleration. Mass times acceleration. So we have that the dimension for mass is capital M. And from what we have done so far, we have that acceleration is length per unit time squared. So this is the dimension for force. Now let's go deeper. Let's go to more complex things. We have pressure. To get the dimension of pressure, of course, we start from the formula. Now, how will you know all these formulas? You know them by just getting used to physics and all its quantities and the things like that. So force, pressure is equal to force per unit area. Force per unit area, force over area. Okay, So from what we have so far, no need to start repeating the steps from first principles. We just start with what we have so far. But if you are given this, you have to spread out force. That force is equal to mass times acceleration and equal to mass times velocity over time. So things like that until you spread it out very well. So force is already mass times length times time raised to power minus 2, and then area is length squared, right? So writing it in a single line now, we have mass, we already have length raised to power 1, then this is length raised to power 2, so minus 2. We are going to solve this bracket, or you just spread this one out, cancel one length, cancel one length. But let's just use indices, law of indices, to solve this. And then with time, minus 2. Now we notice that we collected each quantity, each fundamental quantity that is similar, we collected them together. So that is how to solve this. Equal to mass, length raised to power 1 minus 2 is minus 1, and then time raised to power minus 2. So the dimension for pressure is mass per unit length per unit time squared. So that is how dimensions of physical quantities are gotten. Now let's do one more and then get it in a little bit different way. We have something like energy or work. So energy and work have same units, we can even use same formulas to get them. So energy or work is equal to force times distance. Okay, now we can also use the units of quantities to get their dimensions. So let's write this in terms of units. I know force is in Newton, but when we break down that Newton was made up of kilogram meters per second square. So kilogram to represent the mass. Remember that force is equal to mass times acceleration. So mass is equal to, that is the unit, SI unit is kilogram. Acceleration is meters per second square. So that is why we have that force is kilogram meters per second square. And then times distance, and distance is in meters. So now what I'm just trying to do is just to show another little bit different kind of way to get the dimensions of physical quantity. It will be very, very important later. So if you can remember their units, that's their broken down units, not like something like Newton or Pascal for pressure. If you can remember their units in fundamental quantity form like this. So we know that kilogram is for mass. Okay, let's even collect this together first before we start going to dimensioning. So we have kilogram. Now we have meters squared, because this meter times this meter is still in a single line, like it's not underneath. So it is like multiplication. So meter squared per second square. So we have, for kg is the unit of mass, meters is the unit of length, so length raised to power 2, and then we have seconds is a unit of time, so time raised to power minus 2. So this is another way of getting it, or we can go ahead and then get it the way we usually get it, not from its units. We get it from the formula force times distance, and force is equal to mass length per unit time, mass times length per unit time squared. So we now have that here, and then we now combine it with this distance. Right now, and I believe that we are already familiar with how to get the dimensions of physical quantities, derived quantities. Now we are going to go into the uses of dimensional analysis. And the first one we'll be looking at is dimensional analysis is used to check the correctness of physical equations. And we'll be using this very example to do that. We have this, one of the equations of motion. We have it as sometimes that distance is equal to half a/t squared. I know that ordinarily this is not the full formula, but sometimes we can use just this part of the formula. It's equal to ut plus half at squared. But sometimes initial velocity is 0, and then we now have this. So let's just use this simple one to now get used to how to use dimensioning to verify a physical equation, a physics equation. Now, S is for distance, right? So that is a measurement of length in dimensional form. This is length. Distance is equal to half is a constant. A constant that is dimensionless, so it has no dimension. Now we have acceleration. And from what we did before, we have that acceleration is length per unit time squared. And then we have that time, or let me even write this as fraction so that it spreads out. Now we have that this is distance. Distance by dimension is a measurement of length, right? Very good. Equal to half is a dimensionless constant. And then acceleration is length per time squared, right? And then we have time squared. Time squared, that's multiplication, so it's on top like this, right? Now, when we look at this, in dimensioning, the major aim is to check that the dimension on this left-hand side is equal to the dimension on the right-hand side. That is when and only when we could say that this physical relationship equation is correct. Now, we can see that time squared is down here. It can cancel out time squared up here. And what we are left with in terms of dimension is length is equal to half length. So this half is dimensionless. So we can see that length is equal to length. Therefore, this equation is correct. Now, let's also look at another equation. I'm also using another equation of motion. We have that v square is equal to u square plus 2as, where v is the final velocity, u is the initial velocity, and then this is 2, a dimensionless constant, and we have acceleration and we have distance. So let us write that in terms of dimension. Velocity is equal to length per unit time. That's distance or displacement over time, and it is squared. And then on this side, this is initial velocity, so same unit as this, length squared. No, that's length per unit time, all squared. We have plus, we have 2, which is a constant, dimensionless, so no need. Then acceleration is length per unit time squared. And then we have the distance. Distance is a measurement of length. So we can see that we've represented them in dimension. Now, for this side that has plus, all we have to make sure of is that the dimension of this side is same thing as dimension of this side. That is when and only when we can add up these two quantities. And that the dimension of these terms on the right hand side is equal to the dimension of the terms on the left hand side. So the terms on the left hand side in simple form without the bracket is length squared per unit time squared equal to length squared per unit time squared. So we don't have issue with this speed, this initial velocity. Then it is now here. This is to a constant, it doesn't matter. And then this is length times length, which is equal to length squared. And then under here we have time squared. So we can see that the dimensions of every term in this equation is same thing. Therefore, this equation is valid. So we have seen how to use dimensional analysis to validate physical or physics equations. Now, another use that we are going to be looking at is we are going to be using it to find out the relationship between quantities. We'll be seeing that with an example. Now we have this example. The velocity v of the wave set up by plucking a stretch string is found to depend on the tension T of the string and its length L and its mass M, and it is given by V equal to K, T raised to power X, L raised to power Y, and M raised to power Z, where X, Y, Z are unknown numbers and K is a constant. So remember that from what we've done before, that K, constants are dimensionless. So whenever we see constants, no need to look at dimensions. They are just numbers, just a constant, in which when you do practicals, you can now find out what that constant should be. So now, we have this relationship that v, which is velocity, is equal to a constant, a certain number, times the tension t raised to power x, and then the length raised to power y, and then the mass raised to power z. I'm going to be putting this so as not to confuse this z with 2. Now we shall be representing these physical quantities with their dimensions. For v, which is velocity, dimensionally velocity, that's a measurement of length per unit time. And since we are using, like, this tension is a measurement of, is a kind of force on a rope, that is tension. So force has mass. Therefore, let us include mass here, but mass raised to power 0, because there is no mass for velocity or speed. So this mass raised to power 0, anything raised to power 0, you remember, is equal to 1. So it's just like saying 1 multiply this thing, is just the same thing as just this part. So we didn't really change anything. So that we have something to equate. We have k is just a constant, it remains k, it doesn't change, no dimension. We have tension as a unit of force. So force dimensionally is equal to mass times length per unit time squared. And then remember that this tension or force on a rope is raised to power x. So this whole thing here representing tension is raised to power x. Then we have, this is length, that's easy. We have its length raised to power y, just like it's raised to power y here. Then this is mass, that's also easy. Mass raised to power what? Z. Now I'll be crossing my small letter z so as not to confuse it with 2. Okay. So what we have to do is to open up bracket on this side. So k is k, no units, times m times x, that is outside here, is m raised to power x. And then L times x is L raised to power x, time, which is t raised to power minus 2, so minus 2x. And then here we also have length raised to power y, and then m raised to power z. Now let's collect like terms on this side, because our aim is to equate what is on this side to this side. We have k is constant here, times, we have mass raised to power x, that's, we are done with this mass. Let me use a pencil to cancel out so that we don't miss out on anyone. Now the next mass is mass raised to power z. Since it's multiplication, so it is plus z. Okay, so this is laws of indices. When things in same base are multiplied, we add up their indices. So m raised to power x plus z, and then we are done with m. Let's go over to L. L raised to power x here, and then this is L raised to power y. So since they are multiplying, L raised to power x plus y, and then we are done with L. So let me cancel them out. We are done with L. We picked out all our L values. The remaining thing is t raised to power minus 2x. We have t raised to power minus 2x. There is no other t here to merge it with it. So remember that all these are equal to m raised to power 0, L raised to power 1, of course, and then t raised to power negative 1. Now what we are going to do is, each of these physical quantities, we are going to equate them together. We are going to equate m on this side to m on this side. That is, we are going to be equating their powers. So the powers of m, considering the powers of m, we have that 0 on this side, the power of m is 0 on this side, is equal to the power of m on this side, x plus z. So we are equating powers. So this gives us that x is equal to negative z. That's when we take one of the terms over to this side. We have that. That is when we take z over to this side, we have that plus z goes over to become minus z. 0 is on this side. That's 0 minus z is minus z. So this is what we have from equating the powers of m. Let's keep it aside. You don't know x, you don't know z yet. So we have to equate the powers of length. Now equating the powers of length, we have that on this side we have 1, length is raised to power 1 here, is equal to length raised to power x plus y. So here we don't know x and y, let us leave it as it is. Now we equate the powers of time. We have that time on this side is -1, that's the power of time, and then on this side is equal to -2x. Now finally we have an equation that has just one unknown, so we can start solving from this last one. What we have to do is to isolate x on one side and then send these constants over to this side. So we divide both sides by -2 on this last equation. When we divide both sides by -2, -2 goes away from here, minus cancels minus. We find that x is equal to 1/2, that is half. So we have found x. Now we can take x to the second equation that we have here to find y. And then we take it to this first equation to find z. Okay, so to the second equation we have that 1 is equal to, instead of having x, let us replace it with, we now know the value of x, equal to half plus y. Now we are going to isolate y on this side by sending half over to this side. This leads us to find that 1 minus half, that's half crossing over this equal to sign, becomes minus half, is equal to y. 1 minus half is equal to half. So we have found that y is equal to half, x is equal to half, y is equal to half. Beautiful. Now let's go over to the first equation where we find z. We have that x is equal to -z. And we already have what x is. We have that x is equal to is half, therefore z is equal to minus half. You can see that. Therefore z is equal to -half. So we have found, because the question says we should find x, y, z. They are unknown numbers, so we have to find them. So now we have found them. Then our answers are that x is equal to half, y is equal to half, and z is equal to half. And z is equal to -half. So this is another way of using dimensional analysis. Now I know that the previous example was quite challenging. You could rewind the video and then solve slowly, or pause the video, solve again to be sure. Now we have this one more example that is similar to the previous one. Let's also use it to consolidate what we have learned so far. Okay, we have that the power of wind moving at a speed v is used to turn a turbine of radius r and is given by v is equal to k, which is a constant. This is rho raised to power a, r raised to power b, and v raised to power c, where k is a constant of no dimension, and rho, this is not a small letter p, it is rho, a Greek letter, is density of air. Determine the values of a, b, and c using the method of dimensions. Okay, so let's write out the equation we have here. We have that p power is equal to a constant k, no dimension, rho is written this way, rho raised to power a, r the radius raised to power b, and then v the velocity raised to power c. Now, of course, in solving this kind of question, you already know the drill. The first thing for us to do is to write these physical quantities in their dimension form and then compare each quantity, each dimension of not coefficients this time, the indices of each of the dimensions to the ones on this side. So we have that power is equal to energy per unit time. And energy per unit time, so let's just do that on this side so as not to overwhelm you. Power is equal to energy per time. And we have that energy is equal to force times distance. So force, that's force times distance per time. Okay, so force is equal to mass times length per unit time squared, and then this is times distance, so length squared per unit time squared, that is time raised to power -2, all over time again. So one of the t's, no, this is per unit time, so it is under here. So this is like three t's under here. So power is equal to mass length square, then time raised to power minus 3. Okay, so this is density. Density, I'm doing that one by one. Density is equal to mass over volume. So mass, this is the dimension m, and then volume is length raised to power 3. Okay, so we have it in a single line, that's mass length raised to power minus 3. Okay, radius, of course, is a measurement of length. So for radius, we have that its dimension is just L. And then velocity, we have that the dimension of velocity is equal to length per unit time. So length t raised to power minus 1. Now, since we've gotten this out of the way, we just did it one by one so as to, we are just sure of all the dimensions of the physical quantities. So what we are going to do is we are now going to write this relationship in terms of dimensions. We have that power, which is mass L raised to power 2, and then time raised to power minus 3 is equal to, K is just K, the density, which is M L raised to power minus 3, and it's raised to power A, and then the radius is L raised to power B, because it's just L raised to power B, as we've seen here, and then the velocity is length per unit time, and it's raised to power C. So the next thing for us to do is to open up brackets on the right hand side. So okay, we bring down K. So we have mass raised to power A, length raised to power minus 3A. So we are just multiplying the powers by the power outside. And then times L raised to power B, that's untouched, is not a bracket. And then here we have L raised to power C, and then the T raised to power minus 1 times the C outside. So minus 1C, or just minus C. Now we are going to collect like terms on the right hand side still. So we have that mass is raised to power A. So that one is uncontestable. This looks like 9. So mass raised to power A. Then L, that's the one that has so many things. So we have L raised to power minus 3A is already here. This times you now mean that the powers are going to add up, plus B and then plus C. So we have gathered all the powers of L into one. And then we have T raised to power minus C. Minus 1C and minus C are the same thing. Now we are ready to compare the right hand side with the left hand side. Now comparing the powers of mass. So let me have comparing the powers of mass. I have that mass on the right hand side is raised to power 1, right? So 1 is equal to, the mass on this left hand side is raised to power A. So 1 is equal to A. Beautiful, we've already found the value of A. That A is equal to 1. Good. So comparing the powers of the length, we have that on this side, length is raised to power 2 is equal to, length here is minus 3A plus B plus C. Now we have so many unknowns. Let us just leave it as this. Now for time is raised to power minus 3 on this side. Okay, so minus 3 on this side is equal to minus C on this side. So we can see minus cancel minus, that C is already 3. So we have that C is equal to 3. Okay, so we have found A, we have found C. Now all we have to do is to substitute them into this second equation. So this second equation leads us to find that 2 on this side is equal to minus 3. Instead of A, we should have 1, because A is equal to 1, plus B, we don't know B, plus C, which is 3. So minus 3 times 1 is equal to minus 3. Minus 3 plus minus 3 is equal to 0. So on this side, you just have that 2 is equal to b. Therefore, b is equal to 2. So the solutions are that a is equal to 1, b is equal to 2, and c is equal to 3. So that is what we've been asked to find.